Hi everyone, in this video we are going to cover or go over the solutions to the review problems for the Quiz Friday on section 3.2 and 3.3. And the first thing I'll note, knowing the various forms of the Pythagorean identity, the two in particular that will be needed for the quiz are that the sine squared of theta, or feel free to write it with x's, plus the cosine squared of theta is equal to 1. And then the substitutions we make, right? 1 minus cosine squared theta is sine squared theta, or the other way around. And then the second one is the tangent squared of theta plus 1 is equal to secant squared theta. If you forget that one in a pinch, write down the regular Pythagorean identity and divide each term by cosine squared theta, and that's how you produce the variation. Now, when you look at number one, and for each of these, feel free to pause the video, think about what the substitution is going to be first, and then come back and we can go over it. But you consider the two substitutions. You can set u equal to the tangent of theta or u equal to the secant of theta, and then du is either secant theta tan theta or secant squared theta. And the best substitution, or the one that will be useful here, is setting u equal to the tangent of theta, and then du is tangent of x, because this problem has x's in it, and then du is secant squared x. And like the reason why that's the correct substitution is this guy right here is u to the fourth already, and then my secant squared theta, my secant to the fourth theta, I can write as secant squared theta times secant squared theta. Oh, geez, these should be x's. Secant squared x and secant squared x. And then my secant squared x dx is the du. And this secant squared we can turn into tangents using the Pythagorean identity. And another theta I need to fix over here with my du. That should be secant squared x dx. Okay, two mistakes so far. Try to limit them. So that's kind of the discussion about what is the right u substitution and why. And so then we'll take our integral, and first I'm going to rewrite it with everything before the u substitution with all the tangents and everything. So we have tangent to the fourth x. The first secant squared we're writing as tangent squared x plus 1. And then the second secant squared x stays to be the du in my u substitution. So this becomes du, and all of the tangents are rewritten as u's. So now we make our substitution, and everything is just going to be u's. We've got a u to the fourth, we've got a u squared plus 1, and we have a du. All right, then we simplify before taking the antiderivative. Distribute the u to the fourth, and you get u to the sixth plus u to the fourth du. Now we're all set up to take our antiderivative, u to the seventh over 7 plus u to the fifth over 5 plus our constant c, and then back substitute. That is tangent to the seventh x over 7 plus tangent to the fifth x over 5 plus c. And there's the first one. Moving on to problem number 2. And in this one, we have a definite integral, so we're plugging in some bounds. The thing to like notice and pay attention to is there's a little 2x there. It's not just an x. That just adds like one little degree of difficulty to, thing to pay attention to. And when we consider our substitutions, we're looking for the odd exponent to save that term, that cosine in this case of 2x, to be the du. You're looking for the odd one to save for the du. So we're going to take that cosine to the fifth x and first rewrite our integral 0 to pi over 4. And we're going to go ahead and write this as cosine to the fourth of 2x, sine squared of 2x, 2x, and then cosine 2x dx. And I even spaced it out a little bit because I know that this right here is getting saved for the du. Okay, and then my cosine to the fourth of 2x. Let me change to green. We're going to write that, and we're going to convert that to sines as 1 minus sine squared 2x squared. Right, cosine to the fourth is cosine squared squared. So we take the first cosine squared, write it as 1 minus sine squared, and we still have the other squared. All right, now we're set to make our u substitution, and we set u equal to the sine of 2x, and du is 2 times the cosine of 2x dx. And I'll also consider my bounds right now. For the bottom bound, the sine of 2 times 0, still 0, and the sine of 2 times pi over 4. 2 times pi over 4 is pi over 2. The sine of 90 degrees, pi over 2, is 1. So after our u substitution, our bounds are from 0 to 1. And my 1 minus sine squared squared, 1 minus u squared squared times the next sine squared, that is u squared, and then du. Ooh, one thing I don't want to miss is that 2. This 2 right here gives me a factor of 1/2 out in front of the integral. Okay, and because cosine 2x is what I have underlined there in red. Okay, so now we come to our algebra step. First, we'll square that binomial, 1 minus 2u squared plus u to the fourth, and then we'll distribute the u squared into that parentheses. We have 1/2, and what are we going to have? We're going to have a u squared first, minus 2u to the fourth, plus u to the sixth, and then I close my parentheses, du, keep my bounds, 0 to 1, and so that was just this u squared distributing into each term in the green parentheses. Okay, so now we can do our antiderivative step. Let me just choke this off a little bit. There we go. And we have 1/2 parentheses u cubed over 3, 2u to the fifth over 5, u to the seventh over 7 over our bounds from 0 to 1. And then top bound minus bottom bound, ignore those identities. Those are useful in number 3. 1/2 times a third minus 2/5 plus 1/7. And that was pretty direct to write down because the 1 cubed here is 1. The 1 to the 5th there is 2 times 1. The 1 to the 7th there is 1. And then the bottom bound doesn't give you anything, right? 0 cubed, 0 to the 5th, etc. And then punch all of that into your calculator, convert it to a fraction, and you get 4 over 105 as the value of that definite integral. Now we'll look at number 3. Number 3 requires the identities, one of which is wrong. That should be the sine squared of theta is 1 minus cosine 2 theta over 2. If I give you a question on the quiz, those identities will be provided. I'll put them right with the problem where you need them. And we can just use them directly on this number 3, which I'm going to rewrite just so I have more space. The integral of the cosine squared. Notice that's a 3x. That just, again, adds a little bit of difficulty. Okay. When we apply the identity, cosine squared of theta is 1 plus the cosine of 2 theta, 2 times the angle. The angle in this case is 3x. So 2 times 3x is 6x over 2, and then my dx. So there's our half angle identity applied to simplify this integral or make it integrable, able to integrate more easily. And now the first thing I'll do is ignore the 1/2. It tags along. So the 2 in the denominator comes out of the integral. And then we take our antiderivative of each of these two terms. The antiderivative of 1 is x. The antiderivative of the cosine of 6x is 1/6 the sine of 6x. And then tack on my plus c. You can leave the 1/2 out in front. You could write it in the denominator of the two terms. Either is correct. And so that is the answer to number 3. Now we move on to the back, the 3.3 questions, trig substitution. This first one, I put it on here because it's a good example, but like just a little bit more challenging than I would ask on a quiz. Step one of these trig substitutions, decide what substitution is correct based on that formatting. X squared plus 25, that is a tangent trig substitution. So we go, all right, x is equal to a, in this case 5, times the tangent of theta, then dx is equal to 5 times the secant squared theta of theta d theta. And I will, right off the bat here, draw my lovely right triangle. Here's the theta angle. There's my right angle. And tangent, based on this substitution right here, tangent of theta is opposite over adjacent, and in this case, x over 5. And then my hypotenuse would be the square root of x squared plus 25. Okay, so that's some preliminary work. Now we can make the trig substitution, plug in all the things. Up in the numerator, x cubed is 125 tangent cubed theta. I'm going to put the dx up top too, times the dx substitution is 5 secant squared theta d theta. And then down in the denominator, the square root of x squared, that would be 25 tangent squared theta plus 25. Okay, pause the video if you need to digest where everything went, where everything came from. Now we move on to simplifying. I'm not going to write this step out, but I'll mention it specifically. Down in the denominator, we have the 25 common to both. If I factor that out, it leaves behind tangent squared theta plus 1, which is the purpose of this trig substitution, secant squared theta, allowing us to take this square root. So I'm going to move over to the right here, and up top, nothing happens. 125 tan cubed theta times 5 secant squared theta d theta. But underneath that square root, we have 25 secant squared theta, or 5 secant theta. This allows us to divide the 5s and divide one of the secant squareds out. So let me rewrite what we have left in our integral at this point. We have the 125. I'll factor that out in the next step. We have a tangent cubed theta and a, whoops, not cosine, and a secant theta d theta. Okay, and this is the part where this one is a little bit more challenging than I would put in a quiz, because it also asks you to do stuff from 3.2. Now you have to play around with the exponents and figure out the right u substitution. So this you would not see, this part of this problem you would not see on whatever the quiz is. Okay, so let's see. I'm going to take my 125 out first, times the integral. Now we consider the two possible u substitutions. If I set u equal to the tangent of theta, then I would need du is the secant squared of theta, which we don't have inside of this integral. We just have a secant to the first power. And if I set u equal to the secant of theta, du is a secant theta tan theta d theta, which we can pull a tangent off of that cubed exponent and save the secant theta tan theta to be du. So let me write that out, what I'm kind of saying there. We're planning ahead of time that u is equal to secant theta, then du is secant theta tan theta d theta. Okay, so then that tangent cubed is tangent squared theta times secant theta tan theta d theta. That is all du, and that's a tangent. In order to do the u substitution, I need it to be a secant, so we use the Pythagorean identity from the previous from the front of this review, or from the previous slide, and that tangent theta becomes secant squared theta minus 1 times secant theta tan theta d theta. All right. So then applying our u substitution, 125 tags along, u squared minus 1 du. All the stuff inside of the integral, this is u squared minus 1, and all of that is du. So there's not much left inside after the u substitution. Then we go to 125, use our standard power rule, u cubed over 3 minus u plus your constant. Then we back substitute into secants, because u is secant theta, so 125 times secant cubed theta over 3 minus secant theta plus c. Okay, so we backed one step up, but now we have to go all the way back and write our secants as the original x's, and I'm going to zoom out so I can see my triangle on the left. Okay, so we've got to write those two secants as x's. So if secant is flip over cosine, cosine is adjacent over hypotenuse, 5 over the square root, secant would be hypotenuse over adjacent. So when we write down our answer here, this is 125, and it's going to look messy, but that's okay. I'm going to break that 1/3 off so this looks less ugly, because my secant cubed of theta is x, the square root of x squared plus 25 over 5 to the 3rd power minus the same thing, the square root of x squared plus 25 over 5 to the 1st power, close my parentheses, plus my constant c. And I'm going to leave that one as is because it's fine. It's ugly enough. But that is the answer to this problem. Okay, so this, again, I won't throw anything that combines 3, 2, and 3, 3, but I wanted you to see just, this problem in particular. All right, now moving on to our last one, which is much more direct trig substitution, and the integral is much more direct to evaluate. This, you might look at it and immediately recognize it as inverse sine, and you would be correct. But we're going to derive it using a trig substitution. I'm pretty sure we did this one in class, but here's just another explanation, another look at it. So this right here, 1 minus x squared, tells me that this is a sine trig substitution. X is 1 times the sine of theta. Dx is the cosine of theta, d theta. And again, I will add in my little right triangle. Theta is here. Sine is opposite over hypotenuse, x over 1. And then this leg is the square root of 1 minus x squared. So then we take and apply the trig substitution. The 1 dx up top is cos theta d theta. And in the denominator, we have the square root of 1 minus x squared. X is the sine of theta. So 1 minus sine squared theta. Okay. Underneath the radical sign, 1 minus sine squared is cosine squared theta. So then this integral simplifies to cos theta d theta divided by the square root of cosine squared is cos theta. Oh, hey, this one's much better to evaluate. My cosines divide, and we have the integral of d theta. The integral of 1, the integral of a constant, is theta plus c. And then for this one, it wasn't really necessary to draw the right triangle, but I'd say do it every time. For our, excuse me, for our back substitution in terms of x's, we'll look here. If x is the sine of theta, then theta would be the inverse sine of x plus your constant. Okay, solving that x equals sine theta equation for theta, theta is the inverse sine of x. Okay, and there we have the review for this quiz. If you have any questions about it, or God forbid if I made any mistakes, shoot me an email and I will do my best to get back to you in a timely manner. Thank you for listening. Have a fantastic day.